welcome everyone to this session about partitionable devices and how it puts the dynamic back in dynamic resource allocation. I'm Morten Torkildsen. I work for Google. I've been working on Kubernetes for 7 years now, and the last year, or about the last year on DRA.
Hey, Jan Philip. I joined NVIDIA beginning of the year, and so far I've been focusing on our DRA driver. You might have heard about compute domains, and recently I've been shifting my efforts towards the GPU allocation, so I can tell you some things about dynamic allocation of MIG devices, which makes use of the partitionable devices part of DRA.
Okay, so the reason we care about this is we want to maximize GPU utilization, because GPUs are expensive and scarce, so achieving high utilization is critical. Like idle devices are wasted money. You don't want to buy a lot of expensive GPUs and have them sit idle. But also workloads are diverse. Not all workloads require a full high-end GPU. Some might require hundreds or thousands of them, and some might have enough with just a fraction of a full GPU. The device plugin API that has been used for a while only allows assigning full GPUs, which means that being able to assign like partitions or fractions of the device is difficult. There are tricks to do this, but it still requires a static partitioning of the GPU, which makes it far less useful. And yeah.
Okay, so who of you has used any sharing technology for NVIDIA GPUs, like time slicing, MPS? Okay, yeah. Personally, I've never used time slicing MPS whatsoever, but I'm not going into time slicing here. But I want to kind of compare at the high level why like MPS and MIG, and why MIG is like fundamentally a different game, and why it's actually pretty fascinating technology. So as some of you or most of you know, like MIG partitioning is basically physical partitioning. So MIG multi-instance GPUs, they basically assign every partition their own fraction of actual hardware, meaning that you get proper fault isolation between jobs that are running on the same physical device, and predictable quality of service, and in general, just really predictability and robustness compared to any other of the sharing solutions. Especially in, say, multi-tenant environments, or when bad actors might be your neighbor, like consciously or not, MIG partitioning is just the more sane technology. So how is it done in hardware? Every MIG device on a physical device actually gets their own like streaming multiprocessors, their own specialized engines like copy engines, JPEG encoders and stuff that I don't even know too much about. And the entire information flow, the path between the SMs and a MIG device is assigned like memory regions, is isolated for just that MIG device. So as I said, that results in very well-defined quality of service and fault isolation. And a nice quote I found in NVIDIA's MIG user guide. Well, an individual user's workload can run with predictable throughput and latency, even if other tasks are thrashing their own caches or saturating their memory interfaces. That's why MIG is actually like very compelling technology. Okay.
Okay, yeah, so the old way of doing this is with extended resources. This works by having a device plugin that runs on every node. It discovers the devices on the nodes, and informs the kubelet, or informs the API server about the number of devices for a specific type. And this happens through the node resource. In the example here, you can see that this node object reports 3 GPUs. And then when the scheduler needs to allocate devices for a pod, it simply just looks at the number of requested devices and the number available, and it can quickly decide if this works or not. The way we can do device sharing here is simply by letting the driver report a higher number of devices than is actually available. The drawback of this is that typically this requires static partitioning. So when a node is created or when it's provisioned, someone needs to go in there and partition the GPUs. And typically that also requires that all GPUs must use the same partitioning. This is inflexible and fragile. So in the example here, as you can see, instead of reporting 3 GPUs, now it says we have 24. And the pod that comes in requests 1, and in this case, instead of getting 1 full GPU, it actually gets 1/8 of a GPU. The problem here is somewhat obvious, though. If I suddenly need, or the partitions here have 5 gigabytes of memory. If suddenly I get a workload that requires 10 gigabytes of memory, the physical GPU has enough memory, but I've partitioned all of them into 5 gigabyte chunks, and suddenly I don't have a GPU with the right amount of memory. But we can do better now with DRA. So I'm guessing some of you have already seen this slide a few times before. So what is DRA? It's sort of 4 parts to it. It has an API to describe devices. This is the resource slice API. This is the most important part for this talk. And it allows drivers to describe the devices available and attach capacities and attributes to these devices. So, for example, it's also to say, like, this device has 40 gigabytes of memory. The second part is an API to request devices. This is the resource claim API, and it lets you specify things like, I want an NVIDIA GPU, and it needs to have at least 30 gigabytes of memory. The scheduler plugin matches requests to the available devices, and the Kubernetes API is responsible for actuating the decisions from the scheduler and makes the devices available in the containers. And with the array, we can do dynamic MIG partitioning. However, with the core DRA features, it's not sufficient to do this. And for this reason, we need the partitionable devices DRA extension. And the reason for this is that with MIGs, we have actually dependencies between the different devices advertised by the driver. So in the example here, you can see an example of an A100 and the different profiles. And we can see that different profiles use the same underlying hardware. So if I allocate one device, suddenly other profiles become unavailable. So in this example, you can see that 2 devices have been allocated, and that leads to most of the other profiles to be unavailable. And here's only 6 profiles, which mirrors like 6 DRA devices that are still available to be allocated. Yeah, and to go a little deeper into the partitionable devices feature, it introduces a few new concepts. It's counter sets, counters, and it lets devices consume counters. Important thing here is that this only impacts the resource slice API, so only cluster admins and probably and driver authors need to care about this. There's no changes to the resource claim API, meaning that for workloads who needs devices, they can continue using the same resource claim, and they might get allocated a full device, they might get allocated a partition of a bigger device. It depends on the requirements that's specified through the resource claim. And yeah, a counter set here is a collection of counters. You can think of this as a counter set representing a physical device. Counters represents limited resources on a physical device. So, for example, the amount of memory, the number of individual processors, that kind of things. And a device consumes counters from counter sets. And what makes this solve the problem we described earlier is that devices can only be allocated if sufficient capacity is available on the counters. The partitional devices feature is alpha in 135, and we're planning for beta in 136. And we're trying to go into a simple example here of how this works. So here's an example of a resource slice that defines shared counters. And you can see here we have two counter sets, but we'll focus on counter set 1 here, which we see has 40 gigabytes of memory and 4 CPUs. And as it says on the slide, counter sets must be defined in separate resource slices than devices, but devices can consume counters from any counter set defined in the same resource pool. In the example here, you can actually see that the Gizmo pool has 2 resource slices, so there's another one here. So you have a corresponding resource slice that defines the devices. Here we have one large device, and we can see that it consumes the counters from counter set 1. And in this case, it consumes all 40 gigabytes of memory and all 4 CPUs. We also have a small device that only consumes 20 gigabytes of memory and 2 CPUs. And as you can see below, there's also a second small device that consumes the same amount of counters. And if now the small device 1 gets allocated, this means that the counters consumed by this device is no longer available in that counter set. So we can see on the right here that the available counters now is actually 20 gigabytes of memory and 2 CPUs. And the result of that is that the large device now is no longer available to be allocated because there's just not enough counters left, and this makes sure that the only devices where the underlying hardware is actually available can get allocated. In this slide, it might look like we actually update the resource slices. That does not actually happen. This all happens in the scheduler, which keeps track of the available counters for each counter set and looks at it during the allocation time.
Okay, let's see how all of this looks in action. So in NVIDIA's DRA driver for GPUs, we're making use of that, right? So support for that parts of this landed in 134. The one Kubernetes, which I have been integrating against. And so for dynamic MIG device allocation, we need a few ingredients. It's maybe not, these are implementation details, but I think they're still very interesting. So NVIDIA has the NVML, the NVIDIA management library that we have. It's a C library that we have Go bindings for, maintained by our team, and we can use that to manage all those primitives that you need for like dynamic MIG device allocation. And that most importantly means like on newer GPUs, you can add a runtime, like enable MIG mode for the whole physical device. And you can also disable it again when no process is consuming the GPU anymore. That means at runtime we can like switch full GPUs between MIG mode enabled and MIG mode disabled. That's like, of course, an important prerequisite for diving into this, for building this. What we also have to do, of course, we need to let the scheduler know, or the DRA system know what are the theoretically available MIG devices. It doesn't mean that they are physically available simultaneously at the same time, but just generally possible MIG devices. We announce all these in a meaningful way to the DRA system, to the scheduler, and then which ones of those can actually be allocated at the same time. We model that with the capacities and consumption parameters like counters and counter sets, consumable counters that Morten described before, and I will show an example in a minute. So So what do we really need to do when workload comes in that wants to have a MIG device created? If it lands on a GPU that doesn't have MIG mode enabled so far, we're going to dynamically enable that, and we create that MIG device with the corresponding like NVML API calls. And then when the workload is gone, we're going to clean up after that, meaning that at the very least, we can destroy the MIG device. And if that was the last job on a physical GPU that was using a MIG device, we can also deactivate MIG mode then again to like make the physical GPU available again for regular full GPU non-MIG jobs. So that's the goal. And that's what we've built, at least in a like proof of concept like fashion so far, and will be potentially in that next December release of our driver. If not in the December release, then in the one after that. Quick example, on the left-hand side, there's a shared counter, a new concept from the Partitionable Devices API. It has a name, like the GPU3 counter set, and that has a number of integer values, which is kind of the fine-grained representation of all the different like physical entities contained in that physical GPU, like for example, 152 multiprocessors. And now on the right-hand side, there's a representation of a MIG device and how many of those, like again, integer count-based entities it would consume up on allocation. So for example, on the right-hand side, there would be like a 3G 95GB MIG device, and it would want 72 of these 152 streaming multiprocessors. And then we also, you know, what's not all too important, like we model these memory slices here. It's an implementation detail, pretty important to kind of model the physical placement of MIG devices on the physical device. And how these two are tied together are really by naming convention, right? So the MIG device definition on the right hand ties to the physical device by referring to the same counter set by name. So I hope that's clear. It's actually pretty simple. Like one can talk a lot about that, but it's like okay, let's see. So how to request a device? As Morten said, we didn't want to change anything from the user's point of view. So who of you has ever requested a GPU device with the DRA API, like with resource claim templates? Okay, at least some of you. Okay, yeah. So that part doesn't change at all, except for that tiny little detail where, you know, as a device class name, you put, you put make.nvidia.com, not gpu.nvidia.com. And then for people that have not used resource claim templates before, like a resource claim template gets incarnated into a resource claim for a pod that consumes it, like for every pod that consumes it, right? That's the point of resource claim templates, right? And the cross-reference between a pod and a resource claim template is really just by the name of the template. I've put it here, you know, as a variable just to point out that you choose that name. You can make it meaningful or cryptic. That's up to you. It just has to be the same name. And in this example, I'm also showing kind of the power of cell expressions for maybe not being overly specific in terms of what device you want. So in this case, combining two criteria. One, I want to have at least 40 gigabytes of memory, but I do not want to have that shitty 1G 47G MIG device, because that has a lot of memory but almost no compute. So please don't give me that. I think that's a relevant practical constraint, yeah. It's actually quite nice that you can combine this so expressively. Okay, so I built a quick demo. I wanted to show like certain things and wanted to keep it simple, but you know, one thing that matters in order to make sharing meaningful, like if you know exactly which workload is coming in, then static partitioning might even make sense, right? So dynamic partitioning makes most sense when you don't know quite ahead of time, so what type of work will be incoming. And then if you have the perfect compute-bound jobs that always, you know, use all of the compute components of your GPU at maximum, then it's probably even better to run through them sequentially. So when does all this make sense? You don't know really what's incoming, so stochastic arrivals, you have jobs with varying needs, and each one of these jobs is maybe not fully utilizing everything all the time. So maybe in inference workloads, when you have a long-running job occupying a GPU, but it would kind of do computation based on requests, right? Then there would be idle time in between. So I've tried to kind of model both with, simple approaches. And what I really wanted to show in this little demo is that, first of all, MIG devices get dynamically created and destroyed, which is already nice. But also with this type of dynamic sharing, we can actually increase GPU utilization as compared to running through things sequentially on full GPUs, meaning the same amount of work is done in shorter time. And I don't know, I thought a bit about it, and it might be obvious that static partitioning is always kind of opposing any effort of resource utilization maximization, and the reason really is that the moment you do static partitioning, you create some idle capacity somewhere. It's really the fundamental reason, right? Demo time. Okay, here we go. I warmed this one up because we still need to restart our kubelets every 30 minutes. And we're running on pre-production hardware. I need to reboot the nodes beforehand. Okay. What am I going to show? 50 jobs doing something, some stuff. The type of workload that I roughly tried to describe before. And for starters, I just want to run them, those 50 jobs, on full GPUs. I'm just going to hit enter here. It's deleting, and then now here in this bottom panel, we see in a moment 50 pods incoming, already container creating, 7 running, 34 pending. Okay, so we have 16 full GPUs. Okay, this is a bit of super small, right? You don't need to know you don't need to see the details. The point is in the left-hand side column here, we have a representation of all 16 GPUs. And on the right-hand side, it's a bit top, right? So we're showing the processes running on these 16 GPUs. And right now we see roughly, even if I don't know how big that is, but we see 16 Python 3 processes doing some, it's mainly matrix inversion, singular value decompositioning, some compute on the GPUs. And then center panel, we see some overall memory usage per physical GPU, some temperature. Temperature is maybe a good metric for utilization. They're not really hot right now, so they're not doing a lot. So while I've been talking, half of the jobs are done. Still, some are in the queue. Again, we only have 16 devices. They run through those jobs sequentially. And can you all see the temperatures? They're around 37 degrees Celsius. So, let's just memorize that number for a second. Okay. The last few jobs are now allocated onto these GPUs. And in a few seconds, that amount of work is basically done, right? And then we're going to see that this has taken us about 2 minutes of time, I suppose. Right after that, I will repeat the same thing with dynamically provisioned MIG devices. So I'm just going in here and change that string. It's 500 milliseconds typing latency. Okay, MIG, let's go, boom. First, deleting the old workload, the pods are gone now, and I'm already minimizing that one. Let's have a look at the left side column of this little terminal dashboard. In a moment, we're going to see a bunch of MIG devices are popping up. That's kind of the magic moment. Okay, so for all these jobs, that are kind of randomly, not quite randomly, but they have a certain distribution in terms of memory requirement. And so like there are some 1G, 24 GB MIG devices, but there's also one bigger one here, 4G, 84 gig. On the right-hand side, we see there's now a bunch more processes actually running on these machines, on these GPUs, and also temperature-wise, there are a few more GPUs now actually kind of going beyond like 40 degrees Celsius, and the memory utilization is also higher. And same amount of work as before, and it's done in half the time. That's kind of the point. So for this type of workload, that type of sharing and dynamic allocation of partitions just crunches through the work faster, and that translates into happier users and less money spent. Okay. Thanks.
Yeah. Now, the partitionable devices feature is not only usable for MIGs. There are several other use cases for this. One is local devices with topology constraints. For TPUs, for example, we typically have 4 TPUs per machine, and if we want to allocate in pairs, only some pairs are actually possible. So you can see here the ones that are possible and the ones that are not allowed, and we can model this with partitionable devices so that it's possible to only allocate pairs of 2, or the right pairs, essentially. Another use case for this is multi-host devices, and TPU subslicing is one use case for this. It's a somewhat complicated example, so we're not going to go through that here, but there was actually a talk in KubeCon EU about this exact use case. Yeah, upcoming work around this. So the array does not currently have full support for scoring, so it might at time makes suboptimal decisions. So for each node, it does a first fit search among the available devices. So if you have a device or a workload that asks for 1 gigabyte of memory, and it finds one with 40, it'll say, yeah, that works. And also, when it checks all the different nodes, how good the solution was for each node is not really taken into account. So it might, another place where it might end up choosing a node where you might think there was another node that had a better solution. Scoring would help with this, and that's something we're looking into. Another thing that's coming up is mix-ins. So with like MIGs and partitionable devices, you end up with a lot of devices typically that looks kind of similar. So the resource slices tend to be kind of verbose. Mix-ins allows for defining common aspects of devices in the mix-in, and there's reference from the devices, which makes the resource slices much more compact. Yeah, that was most of what we had. So yeah, please join the device management working group if you want to learn more or contribute to the array, try out the array drivers, try out new features, like partitionable devices is one of many new features that are in alpha or beta for the array. And finally, if you're building the array drivers and think you have use cases for partitionable devices or any of the other features that we're working on, talk to us, give feedback. We want as many use cases as possible to make sure we get this right.
We have quick time for questions, I guess. I hope.
Well, there you go. Quick question. It seemed like the setup and teardown of the MIG was very quick. And just like with anything, profiling your workload is helpful to understand how much speed up you get. Can you talk a little bit about, how efficient it is, and then if anybody's doing like profiling to sort of decide MIG versus full, things like that?
Yeah, sure. I mean, honestly, I spent half of my week last week kind of profiling where we spent the time with the DRA driver, kind of in managing these devices, and obviously there were a few locks that were maybe not placed most fortunately, and so I was glad that I could kind of get it to this, very quick management just to show something for the demo. But I think we all agree that typically jobs should be kind of longer running than just a minute or so, right? And so on modern GPUs, seemingly we can kind of create and destroy MIG devices, I don't know, 100 per 30 seconds or so, which is cool. But in general, that even if it was slower, it should not really matter in a real world environment, I think. Good question, yeah. Any other question?
I have a question.
Sure.
So I'm facing a problem at work with similar kind of workflows to what you demonstrated there, but not using GPUs. They're just using CPUs and memory. We tried using Carpenter to get the right instances for them, but the way they batch things, could dynamic resource allocation, could DRA with partitionable devices work here where I could set up different slices of CPU and memory for the same machine, and that way the different jobs that they're batching could be pooling from those queues and get efficiently scheduled?
It might be possible. There is a proof of concept of a CPU driver for DRA. So it's hard to say right now if that's going to solve your use case, but yeah, happy to talk about it.
Yeah, so we'd need a special driver for it, though. Is that what you're saying?
Yeah.
Yeah, okay.
I mean, I have not really looked at that driver, but there was a nice talk about that CPU allocation driver here also at KubeCon. It seems to be in its infancy, but it seems like what you describe is exactly the type of problem it tries to help with.
Okay, okay. I'll find the video.
Okay, we're done. Thank you.